I'm very excited to be here today, and I want to thank the organizers for allowing me the opportunity to speak here. So this is a work in progress, actually, nothing on the archive yet. It's about basically similar in some ways to what Stephen Jordan was just talking about, which is whether or not you can classically model tunneling, but not via, I guess, simulating the quantum process per se, but I guess simpler algorithms. And this is joint work with Tameem Albash, my colleague at USC, and also Peter Young at UC Santa Cruz. So what is the motivation for this topic? So the motivation is actually that right now we don't have any quantum annealing speedups ever, unfortunately, and there are no examples. If you look at quantum annealers as optimizers, as solvers for optimization problems, then we have no proof whatsoever that they work. And let me tell you why. I guess some people might disagree with that. So, for example, you could come up and say, look, we have adiabatic Grover, quadratic speedup, etc., and variance, and I will say, no, that's not really true because adiabatic Grover is an oracular problem, and so in a sense, the complexity is potentially being swept under the rug, and you need to have an exponential number of terms in your Hamiltonian, and the oracle, is doing something exponential. So when you take everything under consideration, then we can't really say that it's a true algorithm that provides a quantum speedup. So you could also come up to me and say, well, but we have this polynomial equivalence with a gate model due to Aronov et al. And I will say, well, that might be true, but then it requires non-diagonal problem Hamiltonians, and I think Peter Love talked about it with the clock states. So it's basically irrelevant to optimization problems when you think about it. So then you can say, well, we had all these numerical experiments that showed, polynomial, I guess, increase with size for certain SAT problems, but then when you go to higher sizes, you always have crossover to exponential. So even these numerical endeavors have all led to failures. And then you can tell me, well, we have all these beautiful experiments, with the D-wave device and whatnot. And if you look at them one by one, you realize that none of them really show conclusive results as to speed up, to put it mildly. So no real, basically, quantum annealing speedup so far. And even the optimistic results that we've been hearing about lately about observed advantages, numerical or experimental, and there's a quite long list about that, they are either non-existent or they have been demonstrated with respect to only poorly chosen classical competitors. And this is something that has bothered me for quite some time. And then you can ask yourself, well, and I guess Stephen asked this same question a few minutes ago, is tunneling really a resource? We know, do we know that we talk about tunneling, we know that quantum annealing, tunnels, but is it really a computational resource? And we know that there is no, rigorous mathematical answer to this, but it's unclear from the evidence so far if it's, it's even out there without the proof. And so I want to focus on this picture, which I gave it the name, everybody's favorite picture, because last year at AQC it was on every talk, but I haven't seen it in this year's talks, but I wasn't able to attend all the talks, so maybe it was, but clearly it hasn't shown up, I guess, with the same frequency as last year. But anyway, this picture tells you that quantum annealers tunnel through barriers, and whereas thermal annealers jump over barriers, and Wim van Dam actually pointed out a very good point yesterday about the fact that even for quantum tunneling, the height matters. And so this is one aspect of it. But there's another aspect of jumping over versus tunneling, which is if you consider tunneling as quantum annealers allowing the system to be in classically forbidden states, then maybe thermal annealers, like real thermal annealers, do not allow this, or I guess unless you have temperature, then classical solvers, if you look at an algorithm, then they can allow this. I mean, classical solvers on a digital computer will allow you, in a sense, to tunnel. They will allow you to be in classically forbidden, quote-unquote, states. And so you ask yourself, so what are is tunneling a true resource? What are the true resources? And again, I thank Stephen Jordan for reminding us that, we know that interference is a resource. We know that entanglement is a resource, or at least some people think that discord is a resource, etc. And clearly we have massive parallelism. But nothing that we know of that says that tunneling is a resource. So if those things, interference and entanglement, come into play in quantum annealing, then of course we need to study this. But tunneling per se, I am no longer sure about, even though that's the buzzword around quantum annealing. And so in that sense, I want to say something really quickly that in a way digresses, but it, to me, was interesting to find out, which is if you go to density functional theory that talks about electronic structures and, in electrons in metal, etc., it has nothing to do with quantum annealing, and you think about the basic theorems of DFT, it tells you that if you consider electrons running in a potential of ions or atoms, it tells you that no two potentials lead to the same electronic ground state, and also no two ground states lead to the same charge density. And it tells you sort of that the potential says what the charge density is, the charge density tells you everything about the potential, and it basically, the charge density of an electronic wave function tells you everything that you need to know about everything, the entire spectrum of the Hamiltonian. And you can apply DFT to adiabatic quantum computing, and if you consider adiabatic quantum computing going over the ground state, just tracking the instantaneous ground state, then you can say, okay, the potential is sort of the problem Hamiltonian, and you can figure out that no two problem Hamiltonians lead to the same ground state, and also that no two ground states lead to the same probability distribution in the computational basis, in the basis of the potential. So it basically means that there is a one-to-one correspondence between the problem Hamiltonian and the probability distribution. So in a sense, this is like a hand-wavy argument that sort of says that it's a game of probabilities rather than of wave function amplitudes. And we know from quantum mechanics that if it's a game of probabilities and not, interference of the amplitudes, then maybe there's something missing there. But I know this is sort of hand-wavy, but this is sort of something interesting about ground state computation. So then you can ask, can you classically model tunneling? And Stephen showed, quantum Monte Carlo or quantum-inspired algorithms that show, in some sense, tunneling. And I will do the same, but with much, I guess, simpler, well, I guess in terms of success, they're not as successful as what we've seen so far, but much simpler algorithms that sort of, in a way, show you tunneling. And I will explain in a minute what I mean by that. So I can ask myself, well, is there a classical stochastic process? If it's a game of probabilities, is there a classical stochastic process that sort of generates the same probability distributions that quantum annealing generates along the evolution? And I say that the DFT argument, in a way, tells us that, yes, you can, under some conditions, actually generate the probabilities that quantum annealing generates. And it means that, and I'm not talking about the complexity of how it can be done, but at least if it's a game of probabilities, then there is a nonlinear stochastic type thing that you can run, and it gives you the quantum annealing evolution, even though it's a classical algorithm. And to simplify matters, I want to consider just a simulated annealing process. So I'm not simulating quantum mechanics or quantum evolution or quantum Monte Carlo, none of that. I'm just saying, let us consider, so normally people consider simulated annealing, and you flip one bit and something happens, you flip another bit, and then you go down in energy, and if you have temperature, you jump over barriers. Let's consider a simulated annealing process where you are allowed to flip I spins and not just one. And you decide how many spins to flip with basically with probability of 1 over I, 1 over the number of spins that you are to flip. So flipping 1 spin is more probable than flipping 2 spins, etc. And then you flip I spins, and then you accept the flip with the metropolis probability. So this is one type of algorithm you can think of. And now you can sort of compare quantum annealing and standard simulated annealing, and also this clever, and it's, of course, I'm reluctant to call it a clever, it's just a different simulated annealing algorithm, but I will show you in a minute why I want to call it a clever algorithm that allows you multi-bit flips. And then you can consider even a clever squared simulated annealing where you're allowed I bit flips to flip in every move and then follow it by some steepest descent move. This is due to Tameem Albash. It's a nice algorithm. But anyway, you can sort of try these algorithms and track the distance to solution of configurations of these algorithms and what they do as they approach the simulation and as they approach the solution of the problem. And we looked at several different problems, the spike problem and what we like to call the Brady-Van Dam problems that Wim van Dam talked about yesterday, I think it was, and also another problem which we call Van Dam Mosca Vazirani from, yes, 15 years ago, which I'll explain what it is. I don't have much time, but this is, for example, the spike problem where we have, this is the ground state and the spike. And if you look, for example, at a quantum annealer, so at first, you see that, if you look at all the configurations of the computational basis probabilities, that at first they are binomially centered around n over 2 distance from the solution. And when you run the simulation, then what happens? You see the blob of probabilities tunneled through the spike and reach the solution, and it's very nice. And if you do the same thing with simulated annealing, 1-bit flip simulated annealer, well, it gets stuck, but we knew that already. But look at what happens if you do a clever simulated annealing. So you see, it tunnels. So basically, what I'm trying to say is that classical algorithms that are more than 1-bit flip, or they're properly constructed, can tunnel, or at least in this sense. And we have other, I guess, examples. I can't go through all of them, but we can look at the Brady-Van Dam potential with alpha equals 1/2, eventually tunnels, and the simulated annealing does so, but in a poorer way, and a clever simulated annealing tunnels beautifully. So in a sense, you see that these very simple classical algorithms do tunnel. And this is the Van Dam Mosca Vazirani problem, where you have a ground state here and a very close by local minimum, but everything points to the local minimum. And when you run a quantum annealer, well, it fails. It gets stuck over there, and it never appears on the other side. OK, I will stop it right there. And when you do simulated annealing, same thing happens. But when you do the clever, quote-unquote, simulated annealing, look what happens. It tunnels the n bits in one fell swoop. So in a sense, you can do tunneling. It's even sort of, for this problem, it's better than quantum annealing. And since I don't have much time, I wanted to show you some scaling results. I will just sum them all up. So for some of these problems, QA is polynomial, and SA is exponential, but clever SA is also polynomial. And I'll forget about the Brady-Van Dam for now, but for the Van Dam Mosca Vazirani problem, we have an interesting thing that QA and SA both scale exponentially, and clever simulated annealing tunnels better, if you don't mind me saying that, and gives us even polynomial scaling. So just to conclude, I'm just saying that it's unclear whether quantum annealers are qualitatively advantageous to smart classical algorithms. It's unclear, at least to me, that tunneling is a resource. I don't think that at this point we have reasons to be super optimistic. But clearly, quantum has parallelism, interference, entanglement. These are the resources that probably we should focus on. And I would like to, I guess, join Stephen Jordan and others by saying that maybe the answer lies in the stochastic versus non-stochastic question. So that's it. Thank you very much.
Do we have questions for Itay?
Hi. So I would like to say a couple of things. One is, you said at the beginning that in the experiments, the alternatives were poorly chosen.
Yes.
And I disagree.
Not your experiment, but others.
Oh.
No, I'm just kidding.
Yeah, I thought so. So maybe, I would like to try to explain to you why we chose that algorithm.
I honestly didn't target you specifically, but this paper, as long as you brought it up, I mean, I understand that sort of the paper wasn't about speed up in a way, but I also think that it didn't show tunneling in a sense, and so of course I know that the paper itself also mentions other algorithms that are better than the quantum thing. So that's what I meant, that if you really look at a suite of algorithms and not just, you build a problem with clusters, so you know that one bit flip simulated annealing will fail on it, and then you run it with, D-Wave and say, well, it beats simulated annealing. And sort of, I mean, I think, to be fair, you have to do sort of more. But if you want to say D-Wave is not a one-bit flip simulated annealer, then of course that's what it says. But clearly there are other algorithms that can tunnel. So my point is that you have classical algorithms. So I think your paper, in a way, says tunneling is a computational resource, is a quantum computational resource. That's how I interpret it. True. Maybe I was wrong. But what I'm saying is that maybe that's true, but it's not only a quantum resource, it's also a classical resource. Okay?
Well, other than quantum Monte Carlo, I think there are algorithms like in Helmut's paper. They are known to fail for interaction graphs which are sufficiently dense, like the HFS algorithm,
sure,
or even the isoenergetic move, because the percolation threshold will become very low as the interaction graph increases in density. Whereas simulated annealing and quantum Monte Carlo are generic. They are pretty blind,
Right.
They react to the energy landscape, but not to the interaction.
But I think both of these.
We do it that way. But anyway, my question was, if you actually have tried your, clever simulated annealing on those problems.
I honestly have not,
because I think it will fail. So that's.
Okay, I guess Tameem can check this in the next 30 minutes.
That was a brilliant talk. I really loved it. I loved the animations, and I was very impressed with Clever too and Clever. Yeah. And so I wonder, you say tunneling is not a resource, but how about
I'm not saying that. I'm asking that. Okay, so it's. I'm not saying.
How about fake tunneling, like the type of simulated tunneling that you have in Clever 2? That's a resource in that your slopes got better.
Well, that's the thing. So the question. I think the question is tunneling a uniquely quantum resource? And I say, not necessarily, or at least I have a sort of classical algorithms that in a way tunnel. I don't know, you may say, well, it's not really tunneling, but then what is? I mean, to me, to be in a classically forbidden state is tunneling, because that's what when I was a second year graduate student, that's... Yeah, it did. That's, yeah. Maybe it's a unique classical resource. Yeah,
just a short comment. The problems you consider all are Hamming-weight problems.
Yes, that's true.
If you think about spin-glass problems, the direction of finding the direction of tunneling is...
I completely agree. And this is why every time I said clever. And this is because I don't think it's a really, the best clever. I'm just saying that we came up with this, and people think, well, spike problems, quantum annealing, bit simulated. No, it doesn't beat simulated annealing if you just consider 2-bit flips. And that's what sort of rubbed me the wrong way. That simulated annealing is not a 1-bit flip simulated annealing. It's a family of algorithms. And I'm not saying it's the best. I'm just saying it's better for these problems compared to 1-bit flips. That's all I'm saying.
One last question or comment?
Itay, we actually asked ourselves the very same question. Actually, we call it in our group algorithmic tunneling, where you sort of affect these group moves. And we studied it actually quite extensively. And we found, for example, for SAT problems, which I would recommend to throw in earlier than later, and because these spike problems are nice to do some analytical work, but they're highly misleading for a typical optimization problem. I think you already agreed to this. And then we found that for SAT problems, for example, if you do it exhaustively, you take every 5 group of spins and you try whether the flip is beneficial, then maybe not surprisingly, you find you get to lower residual energies, or you get to the ground state faster if you include these group moves. But so absolutely, you can classically emulate tunneling. But as Sergio was alluding to, on a highly connected graph, our argument, even though we haven't shown this conclusively, and this may be a wrong conjecture, but I would expect that on a highly connected graph, there are so many different groups you can meaningfully form that it will be too expensive, while sort of a physical annealer will just sort of feel which direction to go.
I completely agree with you. Except for, I think in the last year's AQC, you in your talk showed a pretty picture of like a parabola with many spikes in it. Do you remember what I'm?
Yeah, what I call the Fakir bowl. Yeah.
Okay. So all of those was like 1-bit flip spikes. And when I saw this, I told myself, look, if you do just 2-bit flip simulated annealing, you will pass through it. And actually, it's your figure that generated this algorithm in a way, because I don't think these spikes that I guess some of you imagine as the tour de force of quantum annealing are the right way to go. But if you widen up the spikes, then definitely there's more to talk about. I certainly agree with you.
All right, so in the interest of time, let's thank Itay again.